Good morning friends, welcome to Turbo Machine classes. I am V. Sushant Kumar, Department of Mechanical Engineering, Angdi Institute of Technology and Management, Belgavi. In today's class, we will discuss about performance characteristics of turbo machine, and in particular, we will discuss about similitude. It is in continuation of the previous class. When you're going for experimentation using the model, suppose say that you want to install a big turbine, so you want to conduct the experiment. You cannot design the original turbine and conduct the experiment. We have to make a model of that and conduct the experiments on the model, and whatever results we get, it is applicable to the original prototype or original engineering design. So when you want to conduct the experiment on a model, then the concept of similitude will come into picture. So similitude is a concept applicable to the testing of engineering models. A model is said to have similitude with a prototype. So prototype means it is actual machine. It is actual machine or structure when both share geometric, kinematic and dynamic similarities. So now what is geometric similitude, kinematic similitude, dynamic similitude? Geometric similitude means the linear dimensions ratios are same. Okay, the ratio of linear dimension on the model and on the prototype should be same everywhere. It should not vary. Okay, that is, the shapes are similar regardless of this size. Okay, if there is a huge turbine, we are going to make a model of the same turbine with a smaller size. Okay, with a scaling ratio, we are going to reduce the size of the turbine, but the shape remains same. So that is meaning of geometrical similitude or similarity. Next is kinematic similitude. So velocity at any point in the model flow must be proportional to the velocity at the corresponding point in the prototype flow. So that is nothing but velocity ratios should be same. Velocity ratios should be same. We can also say that when the velocity ratio are same, velocity triangles representing flow conditions will be similar. Okay, velocity triangles, we'll study that in the next module. And the last one is dynamic similitude. The ratios of different forces are everywhere same. What do you mean by that? All the forces in a model flow must scale by a constant factor to the corresponding forces in the prototype flow. So if you want to test on a model, then it has to satisfy all these three conditions, all these three similitudes. Then only we can conduct, we will get accurate results. If not accurate, at least results which are more acceptable. Let us understand the importance of similitude by considering an example. So usually models are used in the field of aircraft, ships and turbo machinery. For any turbo machine, you want to design and manufacture any turbo machine, we are interested in few relations like head, pressure, flow rate, power, torque, okay, in conjunction with size, speed and properties of the fluid. So in this video class, we will understand the concept of similitude by considering these variables. So here I am considering volume flow rate, head, power, speed, and dimension, the linear dimension d, and the fluid properties such as density, viscosity, elasticity. So I'm going to consider these variables and apply the dimensionless parameter procedure, and I'm going to group them into dimensionless variables, and we will see how it is going to help us in understanding the concept. So in this example, I have considered 8 variables: 1, 2, 3, 4, 5, 6, 7, 8. So there are total 8 variables. So number of variables are 8. Okay. So let us write the dimensions for all these 8 variables. I have written the dimensions for all the 8 variables. If you just look at the dimensions, all of them uh, all the variables contain 3 fundamental dimensions. So number of fundamental dimensions are 3. So total number of variables are 8 and number of fundamental dimensions are 3. So number of pi terms are n minus m. 8 minus 3 is equal to 5. So I can group these variables in such a way that I can get 5 pi terms, means dimensionless groups. I can arrange these into 5 dimensionless groups, which we call them as pi terms. Now let us apply the Buckingham pi theorem procedure here to group them into dimensionless groups. So for that we need to select repeating variables. So the first repeating variable is geometric property. I have taken as dimension d, and the second one is flow property. I have considered speed n, and for fluid property I have considered as density rho. By applying the Buckingham pi theorem procedure, you will get 5 pi terms. I have written the pi terms here: pi 1, pi 2, pi 3, pi 4, and pi 5. So already this concept we have discussed in the previous video lecture. We can just go through that video lecture, or separate video has been made on dimensionless concept. You can watch that video. So here I am just directly considering the results here. So here I have got 5 pi terms. Now let us look into these pi terms, what they indicate. Let us consider the first pi term, that is q by nd cube. This q by nd cube is called as a capacity coefficient, flow coefficient, or it is also called as specific capacity. Now what this ratio indicates, q by nd cube, means what? It means that if there is a turbo machine of fixed diameter and operating at unit speed, it gives us what is the volume flow rate at that condition. So the specific capacity is constant for similar rotors. For example, you consider a fan or pump of certain diameter running at various speeds. It means then the discharge is proportional to the speed. For a fixed diameter rotor, the the volume flow rate of the fluid is proportional to the speed. This we call it as first fan law. We'll study again in depth about this in a later stage. Now let us go further into the discussion. This volume flow rate, I can write it as in terms of velocity and flow area. What is the unit of volume flow rate? Meter cube per second. What is the unit of velocity? It is meters per second. And what is the unit of area? It is meter square. So we get meter cube per second. So I can say that this volume flow rate is proportional to velocity and area. Area means the dimension is d square. Okay, so I can modify this pi 1 term. So pi 1 is equal to q by nd cube. So I can modify this q by n d cube is modified, and I can write it as proportional to v by nd. v by nd. Okay, now what is this nd? We know u is rotor speed is given as pi dn by 60. So pi is constant, 60 is also a constant, so u is proportional to nd. So here I can replace the denominator nd by u. So I have written pi 1 is equal to v by u. Pi 1 is equal to v by u, where v is velocity of the fluid and u is rotor speed. So this ratio we name it by Greek symbol pi, where pi is called as speed ratio. Pi is speed ratio. What is this? It is u by v. So I have inverted this. Actually pi is u by v. What is u? U is tangential velocity of the runner. And what is v? V is the theoretical jet velocity of the fluid. Okay, so now if this pi 1 term q by nd cube, if it is common for several machines, if there are many number of machines and this q by nd cube is common, so it means that they all have the same speed ratio v by u. If q by nd cube is common for several machines, it means that they all have the same speed ratio pi. Speed ratio means v by u. Okay, hence the velocity triangles will be of the same shape. Okay, velocity triangles will be of the same shape. So velocity triangles we will study in the next module. This is the importance of the pi 1 term q by nd cube. Second pi term we got is h by n square d square, where h is head and n is speed and d is dimension. So this ratio we call it as head coefficient or specific head. So it represents the ratio of the kinetic energy of the fluid under the head h to the kinetic energy of the fluid running at the tangential speed of the rotor. So tangential speed of the rotor, so speed of rotor is given as u. What is u? U is pi d n by 60. Okay, so u is proportional to d n. Since pi and 60 are constant, so n square d square, so I can replace this n square d square by u square. Okay, the head coefficient is constant for similar impellers. If there are impellers of the similar type, okay, means same dimension, d will be constant, then the head coefficient is constant for all those impellers. Okay, so for a machine of given impeller diameter, so if there is a turbo machine and its impeller diameter is given, if it is fixed, then what we can derive is the head varies directly as the square of tangential speed of the rotor. Okay, I'll repeat. For a given impeller diameter, head varies directly as the square of tangential speed of the rotor. So this we call it as second fan law. Okay. So here we have pi to term h by n square d square. So as we discussed, n square d square can be replaced by speed of the rotor u. So it is h by u square. Okay, this ratio we represent it by symbol psi, Greek symbol psi. This is about second pi term, head coefficient. You need to remember all these coefficients, okay, flow coefficient, head coefficient, and further whatever we are going to discuss now, power coefficient, Reynolds number, Mach number. We need to remember all these ratios. So the next pi term is p by rho n cube d raised to 5. So this ratio we call it as power coefficient or specific power. So what it represents? It represents the relation between power, fluid density, speed and wheel diameter. So for a given machine, power is directly proportional to the cube of runner or rotor. So if there is a machine of fixed diameter, given diameter, and handling a fluid density rho, then the power P is directly proportional to the cube of the speed of the runner or rotor. So this we call it as third fan law. This statement we call it as third fan law. So I can get this pi 3 term by multiplying pi 1 and pi 2. By multiplying pi 1 and pi 2, flow coefficient and head coefficient terms. If you multiply them, you will get this pi 3 term. Okay, so from the hydraulics we know that the power is directly proportional to the density, volume flow rate and head. So what I can do here is I can modify this. So you know the rules of Buckingham pi theorem. So we can multiply the pi terms, we can divide the pi terms, and we can apply the powers to the pi terms. So we can modify that pi term. So similar thing has been done here. I am dividing the pi 3 by pi 1 and pi 2. Okay, so what is pi 3? Pi 3 is p by rho n cube d raised to 5 and pi 1 is q by nd cube, flow coefficient, and pi 2 is h by n square d square, that is head coefficient. So when I simplify this, I will get p by rho q h. So this is nothing but it is efficiency. P by rho q h is nothing but efficiency, where p is actual power and rho qh is theoretical maximum power available. Okay, so this ratio is efficiency. So this is about power coefficient. We'll again use this in our upcoming video lectures wherever it is necessary. So as of now we have studied 3 pi terms. Fourth pi term is mu by rho n d square. So I can interchange this. I can write it as rho n d square by mu. So we can interchange the pi terms. I told you the rules. We can multiply, divide and add the powers to the pi term. So according to that rule I can interchange this. So I have written it as rho n d square by mu. We know that nd is nothing but it is proportional to rotor speed, and this rotor speed is proportional to velocity of the fluid. So I can replace this nd with v. So my equation will be rho v d by mu. What is this rho v d by mu? It is nothing but Reynolds number. So already this concept of Reynolds number is discussed in the previous video lecture. So you can go and watch there. This Reynolds number, it expresses the ratio of inertia force to the viscous force. In turbo machines, Reynolds number is not such an important parameter because the losses are not just due to viscous effects alone. There are other kinds of losses like shock at the entry, turbulence, impact, leakage are also accounted along with the viscous resistance and friction. And one more reason why it is not very much important in analyzing a turbo machine is, so most of the turbo machines handles fluids like water, air, steam. So wherein the Reynolds number is of the order of 10 raised to 6 or more than that. So in such conditions, the flow is highly turbulent and the performance of machine becomes almost independent of Reynolds number. So for these two reasons, we don't consider Reynolds number so important in analyzing the turbo machines. But machines of different sizes handling oils and other viscous fluids, they undergo efficiency changes at varying load conditions. So for this reason, Moody suggested an equation to determine the turbine efficiencies from experiments on a geometrically similar model. So here I have written the equation. You just have to remember this equation. It is not how it has come is beyond the scope of this syllabus, where n represents efficiency of prototype of diameter d and n suffix m represents efficiency of model of diameter dm. And this equation is valid for the heads below 150 meters. So we have one more equation for above 150 meters, and we have separate equation for the pumps. But as of now, for us, this information is enough to understand. Fifth pi term is E by rho n square d square, where this E is elasticity, rho is density, n is speed, and d is diameter. It can also be written as rho v square by E. So I am not showing all the derivation here. This rho v square by E is called as Mach number. So about this Mach number, we have studied, I have explained about this in my previous video. You can go there and understand the derivation part here. I am directly writing the expression here. So Mach number, importance of Mach number comes and when we consider compressible fluids. When you start studying the compressible fluids, then the Mach number and importance of Mach number comes there. So basically Mach number is ratio of velocity of the fluid to the velocity of sound. Velocity of the fluid to the velocity of sound. This is at this point of time, this information is enough. So when we deal with the compressible fluids, again we will study in detail about the Mach number. So now we have studied all the 5 pi terms. Now let us see the application part of this. For dynamically similar systems, it is not necessary to conduct experiments on full scale system to determine their performance characteristics. Instead of that, we can make the small scale model of that and conduct the experiment on the model. And even on model, it is not necessary to conduct n number of experiments. So here the pi terms dimensionless parameters will play an important role. So you will understand, I'll take up an example. You will understand the importance of these pi terms and importance of similitude. So let us consider the example of a test on a model of centrifugal pump. Centrifugal pump. So we have a centrifugal pump model. We have conducted the experiment and we have plotted a graph of head versus discharge. So I have taken a centrifugal pump model, and for N1 speed I have conducted the experiment and I have plotted the graph. So this is the graph that I got, okay, in the first stage. So now for N2 speed, again you need not have to conduct the experiment. So from whatever graph I got for N1 and using the concept of similitude, I can get the head and discharge for the same centrifugal pump at N2 speed. How? We will see that now. Okay, so we know from the similitude, let me consider flow coefficient. Okay, so I want to find the discharge and head at speed N2. So what I can do is, let us consider the flow coefficient. Flow coefficient is nothing but Q by N dq. So I will apply this at 2 points, at 1 and 2 point. I'll call this as point number 1, this as point number 2. So Q2 by N2 dq is equal to Q1 by N1 dq. Since we are using the same centrifugal pump, so the diameter get cancels. So what remains is Q2 by N2 divided by Q1 by N1. Okay, so we know discharge Q1, volume flow rate Q1, and the speed N1, and we know N2. So I can find Q2 here. Q2 is equal to Q1 by N2 by N1. Similarly, let us consider the head coefficient h by n square d square. So let us consider at point 1 and 2, I'll get h2 by n2 square d2 square equal to h1 by n1 square d1 square. And since the same centrifugal pump I am using, the diameter will not come into picture. So what remains is h2 by n2 square is equal to h1 by n1 square. So we know n1, we know h1, and we also know n2 at what speed. Only unknown is h2. So h2 expression is also written. Okay, since speed n1 and n2 are known, along with the head and discharge at point 1, one can easily calculate the head and discharge at point 2. Okay, so this is for N2. Similar fashion, we can also find discharge and head for other speeds. For example, N3 speed, if I say it as C, we can follow the similar procedure. Wherever 2 is there, you can replace that with the suffix 3. Okay, we can find Q3 and H3. So this is how the similitude will help us in reducing the time of analysis, and it helps us in avoiding repeating the experiments. I hope that you understood this example, and you can appreciate the beauty of Buckingham pi theorem, and that is nothing but dimensionless parameters and similitude concept. In today's class we discussed about similitude. What is similitude and types of similitude? We have three types. One is the geometric similitude, second one is the kinematic similitude, and the third one is dynamic similitude. If you are going for experimentation using the model, then it has to satisfy all the three similitudes. To understand this similitude, we considered few variables and applied the Buckingham pi theorem, and we got pi terms, and we understood what that each pi term indicates, and at last we applied that pi term considering a centrifugal pump example, and applied a capacity coefficient and head coefficient, and understood the graph. So basically we got five pi terms. The first one is q by nd cube, which we call it as capacity coefficient, and second one is h by n square d square, it is called a head coefficient, and the third one is p by rho n cube d raised to 5, which we call it as power coefficient, and the fourth one is Reynolds number, and the last one is Mach number. So for any doubts, feel free to contact me, and thank you for watching the video.